Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 11 of the NPTEL MOOCs course on economic growth and development. In today's lecture we will be studying the basic Solow model, and one of the characteristic features of the Solow model is that it has made one of the biggest contributions to the neoclassical theories of economic growth and to the understanding of why the rich countries are so and how the poor countries can catch up with the richer countries. Speaking at the annual meeting of the American Economic Association in 1989, economic historian David Landes chose as the title of his address the fundamental question of economic growth and development, that why are we so rich and they so poor? And this question has preoccupied the minds of economists for a very long period of time. The modern examination of the growth question by macroeconomists dates back to the 1950s, and the publication of two famous papers by Professor Robert Solow of the Massachusetts Institute of Technology. Solow's theories basically helped clarify the role of physical capital accumulation and the role of technology as the ultimate driving force behind sustained economic growth. Now, during the 1960s and to a lesser extent during the 1970s, work on economic growth flourished. For methodological reasons, however, important aspects of theoretical exploration of technological expansion or technological progress were postponed. In the early 1980s, work at the University of Chicago by Professors Paul Romer and Robert Lucas reignited the interest of macroeconomics or macroeconomists in economic growth, emphasizing on the economics of ideas and human capital or human capital formation. Taking advantage of the theory of imperfect competition, Romer introduced the economics of technology to macroeconomists, and following these theoretical advances, various empirical exercises were carried out by economists such as Robert Barrow of Harvard University, who quantified and tested theories of economic growth. And since then, both theoretical and empirical work on economic growth has increased and has been sustained with a lot of professional interest. Now, one of the things that we have been discussing in the last few classes is with respect to the different shapes and sizes of different economies of the world. So, world consists of economies of all shapes and sizes, and we know that some countries are very rich, some countries are very poor, and some countries are caught within these extremes of rich and poor. And based on empirical studies of various countries, some stylized facts with respect to growth and development have been worked on. Before we move on with the basic Solow model, it makes sense to start with these certain stylized facts of growth and development. Why I call them stylized is that, or why economists call them stylized is that, these are all facts which are backed by empirical data, which is supported by empirical data, and on an average stands true for various countries across the world. Now let us have a look at some of the stylized facts, and it is important that we keep this in mind when studying growth models in general. One of the first stylized fact is that there is enormous variation in per capita income across economies. The poorest countries have per capita incomes that are about less than 5% of per capita incomes in the richest countries, and the 5% estimate here refers largely to the period of the 20th century, and this variation in income has been seen largely in the 20th century. And the stylized facts that we see with respect to the growth models are largely based upon the empirical data of the 20th century. The second fact is that rates of economic growth vary substantially across countries, and this is something that is implicit in fact number 1. The third is that growth rates are generally not constant over time. For the world as a whole, growth rates were close to zero over most of history, but have increased sharply in the 20th century. For individual countries, growth rates also change over time, and this is evident from the discussion that we have had in the earlier classes with respect to Simon Kuznets' empirical studies on growth or growth of countries or income growth of countries over a period of time, which based upon historical data he concluded that the industrialized countries of the world seems to have grown at a very rapid pace largely in the 20th century compared to the historical growth rates. The fourth stylized fact is that a country's relative position in the world distribution of per capita incomes is not immutable, which means that countries that are poor today may become rich tomorrow and vice versa. So there is nothing immutable about the distribution of per capita incomes and the relative position of the countries in world distribution of incomes. The fifth stylized fact relates to the so-called most powerful country of the world today, the United States. And the growth story of United States over the last 20th century has been highly celebrated, it has been highly cited. However, there are certain characteristic features of this growth story that has emerged based upon empirical analysis, and these characteristic features largely refer to the pre-2008 financial crisis period, and they are as follows. First, that the real rate of return to capital R shows no trend upward or downward. In other words, the real rate of return to capital does not seem to be having any trend. The second is that the shares of income devoted to capital R into K by Y and labor W into L by Y show no trend. In other words, we do not know whether the share of income devoted to capital or labor is rising or declining. And the third, the most important, is that the average growth rate of output per person has been positive and relatively constant over time, which means that United States exhibits steady, sustained per capita income growth. And this is an important finding relating to the developed countries of the world. The sixth stylized fact is that growth in output and growth in the volume of international trade are closely related. And if you recall our discussion regarding the structural features, characteristics of the developed and the underdeveloped countries, you would see that you would remember that the mix of commodities which are internationally traded is one of the important characteristic of developed countries. The developed countries seem to have a mix of commodities which has a very high incidence of manufactured goods, and one of the stylized facts based upon empirical data also tells us that growth in output and growth in volume of international trade are closely related, which means that higher the growth in international trade, higher the growth of output and higher the growth of income or economic growth of a country. The seventh stylized fact is that both skilled and unskilled workers tend to migrate from poor to rich countries or regions, or there is labor mobility between the countries or regions, and it is mostly the migration is usually seen from the poorer countries to the richer countries or richer regions of the world. So these stylized facts that we have just seen generates a lot of interest in growth theories with respect to economic policies, and surveying these kinds of evidence with respect to economic growth. In the 1985 Marshall Lecture at Cambridge University, Robert Lucas Jr. expressed the sentiment that fueled research on economic growth for the decade of the 1990s, and he said something like this. He said that I do not see how one can look at figures like these without seeing them as representing possibilities. Is there some action government of India could take that would lead the Indian economy to grow like Indonesia's or Egypt's? If so, what exactly? And if not, what is it about the nature of India that makes it so? the consequences for human welfare involved in questions like these are simply staggering. Once one starts to think about them, it is hard to think about anything else. So basically he was trying to say that all of these empirical facts, bagged, stylized facts tell us that why the different countries across the world have been growing at different pace, why the rates of growth have been different for different countries across the world, and if all of these growth rates could be mathematically determined based upon what variables could be increased by what proportions, then why is it that in spite of making attempts towards that, some countries still lag behind the rest? For example, the Asian miracle countries like South Korea have grown rapidly over the period of the 1980s, whereas the South Asian countries have lagged behind. Therefore, in this context, it is important to understand what are the structural characteristics of certain countries, or is it the structural characteristics of certain countries that make them relatively backward than the rest of the countries. So in 1956, Robert Solow, he published a seminal paper on economic growth and development titled A Contribution to the Theory of Economic Growth. And for this work and many of his subsequent work after this, he was awarded the Nobel Prize in Economics in 1987. And in this lecture, let us develop the model proposed by Solow and explore its ability to explain some of these stylized facts that we have just discussed. It has actually been claimed that Solow model provides an important cornerstone for understanding why some countries flourish while others are impoverished. Before we proceed, let us understand a few things about an economic model. And since we are dealing with models here, every model has certain assumptions, every economic model has certain heroic assumptions made. Let us see what Solow himself talked about assumptions here. He says that in 1956 he wrote that all theory depends on assumptions which are not quite true, and that is what makes it theory. And the art of successful theorizing is to make the inevitable, simplifying assumptions in such a way that the final results are not very sensitive. So certain assumptions are bound to take place in any model so as to come up with some predictions or implications with respect to the solutions that we are attempting. Now a little word about economic models. In modern economics, a model is basically a mathematical representation of some aspect of the economy. You can think of such an economy as toy economies constituting of various kinds of robots, and we specify exactly how these robots behave, which is typically to maximize their utility. Now we also specify the constraints the robots face to be able to maximize their utility. For example, the robots that populate our economy might want to consume as much output as possible, but they are limited in how much output that they can produce because of the given levels of technology within the economy or the techniques of production that are at their disposal. And the best models often are very simple, and they convey enormous insights into how the world works. So for example, consider the supply and demand model of microeconomics, frameworks of that we generally use in microeconomics. They are very simple frameworks, yet they are highly effective in explaining to us the changes in prices and quantities demanded of such varied goods such as the healthcare sector or computers or nuclear technology that respond to changes in the changes in the economic environment. So with this understanding of how and why economists develop models, let us highlight some of the important assumptions that we need to make with respect to the Solow model in our case. These are some of the important assumptions of the basic Solow model. Let me also make it very clear here that in this lecture we are attempting a basic Solow model, and notice that I am using the term basic Solow model because Solow in his original paper came up with a very basic understanding of how the economic growth takes place or how steady state equilibrium takes place in the economy. What is the steady state value of output per worker? What is the steady state value of capital per worker, and so on. However, various extensions and improvements have been made to the basic Solo model to come up with many sophisticated tools of economic growth models. For example, the Solo SWAN model, which is an extension of the Solo model. Various parameters such as technology have been, variables such as technology has been added onto the basic Solo model to tell us how sustainable the economic growth that has been attempted based upon the basic Solo model is. However, in this lecture we are looking at only the basic Solo model. What are the basic equations that are required to formulate the basic Solo model? How does one arrive at the steady state equilibrium value? And what is the implication of the steady state value that we are talking about? So that is the topic of this class's discussion. So let us look at some of the assumptions of the Solo model. The first assumption that we are considering here is that in this model the economy is producing only a single homogeneous good or a composite good. Only one good is being produced, and conceptually if we have to test this model using empirical data, we can very conveniently think of this output as units of a country's GDP. Why? Because GDP, as we know, is a composite indicator which is constructed using data for all goods and services that is produced within the economy. So, and if GDP is a composite indicator, this model can be tested using GDP as an indicator. So it makes sense to make the assumption that the economy is producing only a single homogeneous good. And because the economy is producing only a single homogeneous good, it is implicit in the first assumption that this is a closed model. There is no international trade because there is only a single good. Technology is exogenous, that is, the technology available to firms in this simple world is unaffected by the actions of the firms, including research and development. It is important that we mention here that much progress in economics has been made by creating a very simple world and then seeing how it behaves and misbehaves. And a common problem in economics is for an individual to decide how much to consume today and how much to save for, what fraction of the income needs to be saved for the future. Another is for individuals to decide how much time to spend going to school, accumulating skills, and how much time to spend working in the labor market. So instead of writing these problems down formally, we will always assume that individuals save a constant fraction of their income as savings and spend a constant fraction of their time in accumulating skills. So these are extremely useful simplifications, and without them the models that we use will be difficult to solve because there will be a need for more advanced mathematical techniques, and for various purposes these are very fine assumptions to make, and this will help us run through a very basic model of economic growth. So these are the assumptions that we can consider as given. Now being armed with these assumptions, let us now look at the basic Solo model. Now the Solo model is built around two equations. One is a production function equation and another is a capital accumulation equation. We will come to the capital accumulation equation in some time. Let us spend some time on the production function equation. So this function basically describes how inputs, various inputs are combined to produce a given level of output. Various inputs, say for example how bulldozers, semiconductors, engineers and steel workers are combined to produce output. We usually simplify the production function. So to simplify the model, we group these inputs into two categories: capital denoted by K, labor denoted by L, and output denoted as Y. So here we are showing a function, output as a function of capital and labor, and this production function is assumed to have the Cobb-Douglas form and is given by Y is equal to f of KL, K alpha, L 1 minus alpha, where alpha is some number between 0 and 1. And you have to note here that this Cobb-Douglas production function exhibits constant returns to scale, which basically means that if all the inputs are doubled, output will exactly double. So in this example, capital and labor are increased by some amount A and L, and output also changes by the amount A. So the production function used in the Solow model is of the Cobb-Douglas form, and it exhibits constant returns to scale. Now, to take this idea forward, we have also assumed that the production in this economy is taking place in a perfectly competitive framework. Firms in this economy pay workers a wage, which is W, for each unit of labor, and the firms pay a rent on a unit of capital for one period, which is denoted by R. So this is the rent that is paid on capital, and this is the wage, that is W, which is paid to the laborers. Now we have assumed that there are large numbers of firms in this economy and perfect competition prevails, and therefore firms are price takers. So it is safe to assume that we normalize the price of output in our economy to unity. And so what are the firms doing? The firms are basically solving a profit maximization function here. So they are solving this following constraint here. They are maximizing how to maximize this equation f of KL minus RK WL given the endowments of capital and labor. So according to the first order conditions for this problem, firms will hire labor until the marginal product of labor is equal to wage, and they will rent capital until the marginal product of capital is equal to the rent of to the rental price. So the partial derivatives of with respect to labor gives us this wage rate is equal to 1 minus alpha YL, and the first order derivative, partial derivative with respect to capital gives us R, which is equal to alpha YK. This can be written in this form, WL plus RK. So what is this? This is basically the total output Y of the economy being distributed as wages to labor and rent on capital. So which means that the payments to inputs, or so you can also say that these are factor payments So the payments to inputs or factor payments completely exhaust the value of this output produced, so that in this economy there are no economic profits to be earned, and this important result is a general property of production functions with constant returns to scale. You can also notice here that the share of output paid to labor is 1 minus alpha, and the share paid to capital is alpha, and these factor shares are constant over time. And if you recall the stylized facts that we considered in the beginning of this lecture, you will know that what we are typically interested in explaining is in terms of output per worker or per capita output. So with this interest in mind, we can write the production function in terms of output per worker, where Y is equal to Y by L, and capital per worker K is equal to K by L. So this can be plotted in terms of a production function, Y is equal to K alpha. So this is the production function, this curve is a production function. The x-axis shows us capital per worker, this shows capital per worker, and the y-axis shows us output per worker, and this production function you would see is rising upwards and then become convex to the x-axis. So what this the shape of the production function tells us is that with more capital per worker, firms are producing more output per worker. However, there are diminishing returns to capital per worker, because when we give each additional unit of capital we give to a single worker, it increases the output of that worker by less and less. So which means that the production function exhibits diminishing returns of capital per worker. So this is the first equation, the production function equation of the Solow growth model. Let us just summarize it once again. So we began with this production function, a simplified production function. It takes the Cobb-Douglas form, exhibiting constant returns to scale. So the firms are price takers. So we have normalized price of output in our economy to unity. and the firms are maximizing profits. So they are solving this problem, they are maximizing this function given the endowments of capital and labor. And based on this, we also come to see that the total output in the economy is basically given out as factor payments to labor and capital. So we get this equation WL plus RK is equal to Y. The share of output paid to labor is 1 minus alpha, and the share of output paid to capital is alpha. And these factor shares given the Cobb-Douglas production function are constant over time. And based on that, we also we can see what is the general shape of the production function. And the shape of the production function that we are considering is that which shows diminishing marginal productivity of capital per worker over time. So which means that as with time, when firms produce more output per worker, there is diminishing returns to capital per worker. So each additional unit of capital we give to a single worker increases the output of that worker by less and less. So that's the production function equation. Next we come to the capital accumulation equation, which is a very important equation in the Solow model, and it will also be of interest to know that the Solow model's emphasis on capital accumulation as one of the determining factors of economic growth in countries has also given it the name of a capital accumulation model. The Solow model is also known as a capital accumulation model. So the second equation here, the second key equation of the Solow model is the capital accumulation equation, and this describes how capital accumulates. So the capital accumulation equation is given by K dot is equal to Sy minus dk. Now so this equation has three terms. The first term K dot, second term Sy, and the third term dk. So according to this equation, the change in capital stock K dot is equal to the amount of gross investment Sy minus the amount of depreciation that occurs during the production process, which is dk. And this term K dot is basically a continuous time version of capital. So it is basically saying how much capital has changed over a period of time. So let's say we begin with some capital in time t. So it is the difference of capital in time t plus 1 minus capital in time t. So it is basically talking about the change in capital stock per period, and we usually use a dot notation to denote a derivative with respect to time. So this K dot is telling us how much capital stock has changed over a period of time, and so this K dot is basically dk by dt. It is showing how much capital has changed over a period of time. The second term Sy, as I've already said, represents gross investments, and following Solow, we have assumed that the workers or the consumers save a fraction of constant fraction S of their combined wage and rental income. Y is equal to W plus RK. So we can also say, so we know that Y is equal to W plus RK, and some fraction S of this is saved in the form of is saved by the workers in Solow model. However, it is also important to know that in the Solow model, all consumers are also workers. So they are all working all the time, and so whatever is being saved is ultimately invested. So that is a savings income identity, savings investment identity. Whatever is being saved is all being invested, because all the workers are working all the time, the consumers are working all the time. So the consumers are basically workers, they draw a wage. And it is not hard to understand this assumption. Again, if you recall the structural characteristics of the developed and the underdeveloped countries, one of the features was that the developed countries have a very high worker population, or a large share of their population is in the workforce, unlike the underdeveloped countries. So in this model, it is being assumed that all consumers are basically workers. So there is no scope for increased consumption in this economy. Whatever is being saved is invested, and therefore there is a lot of capital accumulation that is taking place. So this Sy basically shows that a fraction S of income is saved, and the economy is closed as I have just said. So savings equals investment, and the only use of investment in this economy is to accumulate capital, and the consumers then rent this capital to firms for use in production. So that's the second term, gross investments. The third term, DK, here reflects the depreciation of capital stock that occurs during production, and the standard functional form here used here implies that a constant fraction D of the capital stock depreciates every period regardless of how much output is produced. Often in macroeconomics we assume D is equal to 0.05, which means that 5% of the machine and factors used in our model depreciate every year. So 5% is generally taken as an average of depreciation regardless of how much output is produced in an economy. Now because we are developing the Solow model here, for simplicity we can also rewrite this equation as K is equal to Sy by neglecting the role of depreciation here, just to keep this simple. However, we can continue with depreciation in the equation and then move ahead. Now this is the second key equation of the Solow model, but we need to move ahead of this and understand how the evolution of output per person in the economy take place. So we rewrite the capital accumulation equation in terms of capital per person. So here we are talking about capital accumulation only in terms of the investment made. There is no scope for including population growth here. So the capital accumulation will obviously change when we add population to this equation. So this equation needs to be rewritten in terms of capital per person. What will happen then? Then what will happen is that the production function will tell us the amount of output per person produced for whatever capital stock per person is present in the economy. So for that we first need to consider the growth rate of labor force in the economy, and population growth is considered exogenously in this model. So an important assumption here is that labor force participation rate is constant and the population growth rate is given by the parameter n. So if n is equal to 0.01, then population and labor force are growing at 1% per year, and this is shown in the form of an exponential growth, and this exponential growth can be seen in this relationship. So this is growth of population in time t given by L0 E N t. So population growing between the time period 0 to time t. Now so this is the population growth equation. Now we need to combine all of these equations. So we have seen a production function equation, we have seen a capital accumulation equation, and we have seen the population growth rate in the economy. Now we need to combine all of these equations to come up with the capital accumulation per worker in this economy. So to be able to do that, let us first bring all the equations on one slide. So the first equation, K is equal to Sy. We have removed depreciation from this equation. However, depreciation can very well be a part of this. This has been done just to keep this derivation simple here in this lecture. The second is a production function where output is a function of capital and labor. So if we substitute 2 in 1, we get this functional form where K is equal to S F of KL. We already know that the population growth rate takes this functional form. So if we substitute the value of 4 in 3, we get the functional form which reads like this: K is equal to SF K L 0 ENT. So this is capital accumulation, which is accounting for gross investments as well as population growth rate. So this is capital accumulation per worker. However, we have to now differentiate this equation with respect to time to be able to see how over time, how does the capital accumulation per worker equation read like. So for this, we need to differentiate with respect to time, and here Solow introduces a new variable which is basically the capital labor ratio. K is equal to small k is equal to K by L. So if we rewrite this equation, it would read like this: K is equal to, so capital stock is equal to K into L0 ENT. So we differentiate this equation with respect to time, and after having done so, we come up with this most important function of the Solow model, where capital accumulation per worker, so K, the small k is capital accumulation per worker, and that is determined by two terms here. One is investment per worker, and the other is population growth rate here. So SFK1 shows investment per worker. What is the effect of investment per worker on capital accumulation per worker, and NK tells us what is the effect of population growth on capital accumulation per worker. And based on this equation, one of the first, this relationship says that when investment increases, when this term S of K1 increases, then this investment per worker increases, then capital accumulation per worker will also increase. However, when population growth rate increases, capital accumulation per worker will decline. If we had depreciation as a third term in this equation, we would have known that if depreciation increases over a period of time, then capital accumulation per worker would also decline. So investment per worker has a positive influence on capital accumulation per worker, and population growth rate and depreciation has a negative impact on capital accumulation per worker. Now this equation, this is the most important equation of the basic Solow model, and this can also be explained in the form of a diagram, which is a basic Solow diagram. To be able to come to the diagram, let us reframe the questions in a more coherent manner. So the basic problem that we are concerned with is, if an economy starts out with a given stock of capital per worker, say K0, and a given population growth rate, depreciation rate and investment rate, then there are two fundamental questions that come up. The first question is, how does output per worker evolve over time in this economy, or how does the economy grow? And the second question is, how does output per worker compare in the long run between two economies that have different investment rates? So these questions are best answered in a Solow diagram, and this is a standard Solow diagram. For the time being, I would ask you to ignore the production function curve and concentrate only on these two curves, the gross investments curve and the constant capital labor ratio. This is the investment rate with when capital labor ratio is changing, and this is the investment rate that is required to maintain a constant capital labor ratio. So this is the basic Solow diagram consisting of two curves, I equals S of K, or this can also be written as we have derived as K is equal to S F K1, and this is the NK curve. So the first curve, this curve, I is equal to SFK, is basically the amount of investment per person, or this curve has the same shape as the production function that we have seen earlier. However, the only difference is that this curve is translated in terms of amount of investment taking place in the economy. The second curve is the line NK, and this represents the amount of new investment per person which is required to keep the amount of capital per worker constant. Now we have not included depreciation in this figure here. However, we have already understood that depreciation and a growing workforce tend to reduce the amount of capital per person in the economy. Now what we need to do to be able to evaluate the steady state value in the Solow model is to be able to calculate the difference between these two curves, the difference between ISFK and IRNK. So the difference in these two curves, what are the difference in these two curves tell us? It tells us what is the change in the amount of capital per worker. So this difference basically tells us what is the change in the amount of capital per worker. The intuition is that when the difference in this change is positive and the economy is increasing its capital per worker, which is basically the phase below this point of equilibrium. Let us say this is the point E. So below this point E, this is the point where the change is positive, the economy is increasing and its capital per worker is increasing. We say that capital deepening takes place. So this is the phase of capital deepening. This is the phase of capital deepening, and when this per worker change is 0 but the actual capital stock K is growing because of population growth, then we say that capital widening is taking place. So to the right of this equilibrium point E, we say that capital widening take place. So consider this diagram again. Suppose an economy has capital equal to K1 today. Now what happens over time? Consider only these two figures, I equals SFK and the figure curve IR is equal to NK. And we have started with this position K1, which is the amount of capital labor ratio that we have today. So this it's equal to K1. So now we need to know what happens over time. At K1, the amount of investment per worker, which is this, the amount of investment per worker, the amount of investment per worker exceeds the amount needed to keep the capital per worker constant. So this is the amount of investment needed to keep capital per worker constant, and this is the actual amount of investment per worker which is taking place in the economy. So in other words, the amount of investment per worker exceeds the amount needed to keep capital per worker constant. So capital deepening is taking place, which means that K will increase over time. K will continue to increase over time, and this capital deepening will continue until K is equal to K star, at which these two curves are equal to each other, so that K is equal to 0, and at this point the amount of capital per worker remains constant, and we call this point E as the steady state. So this is the steady state point in the solo economy. Similarly, the question arises, what would happen if instead the economy began with a capital stock per worker larger than K star and let's say K2. So at points to the right of K star, so all of these points to the right of K star, the amount of investment per worker provided by the economy is less. So this is the investment per worker provided by the economy. It is less than the investment per worker required to keep the capital labor ratio constant. So the term K is negative here, and therefore the amount of capital per worker begins to decline in this economy, and this decline, the capital widening process, this decline takes place until it falls back to K star. So the Solow diagram basically determines what is the steady state value of capital per worker, and we can also juxtapose the production function equation in this model, which is y is equal to f of k. If we bring the production function curve here, we will basically be able to find out what is the output per labor given the amount of investment required to maintain the capital labor ratio. So after juxtaposing the production function curve here, you can note that the steady state consumption per worker is then given by this, so we are basically finding out the steady state consumption per worker when we are looking at the production function, and the steady state consumption per worker is given by the difference between steady state output per worker, let's say OY star, which is the output per worker, and the steady state investment per worker, which is OI star. So this is the amount of consumption per worker taking place in the economy if we juxtapose the production function into the basic Solow model. So the basic Solow model at the steady state equilibrium point basically is able to give us K star, Y star, I star, and the difference between Y star and I star. So it is basically telling us what is the investment required per worker, the capital required per worker, the output required per worker, and what is the steady state consumption per worker that can take place at the steady state equilibrium point. This in a nutshell is the basic Solow model, in which the capital accumulation equation and the production function equation are brought together by giving a functional form to population growth rate, and the capital accumulation equation is differentiated with respect to time to be able to come up with the capital accumulation per worker, which is basically based upon how much investment per worker takes place with a changing capital labor ratio, and how much investment needs to take place to keep the capital labor ratio constant. And when these two curves meet, we say that the steady state equilibrium is reached. However, what happens to per capita income in an economy when there are sudden shocks in the economy? So that can also be considered by bringing about certain changes to the basic Solow model. And the shocks that we can consider are, this is referred to as comparative statics, where the shocks that we will consider are increase in investment rate S and the increase in population growth rate. So that's how the steady state equilibrium can change, either through the capital deepening process or the capital widening process. So we can either change the investment rate of the economy, or we can change the population growth rate in the economy. So let us first consider an increase in investment rate of the economy. It's the same model that we have considered in the last diagram. So this is the basic Solow model, where I1 is the investment rate per worker given the change in capital labor ratio, and IR is the investment rate required to keep the capital worker ratio constant, and K1 star is the initial point of equilibrium, the steady state point of equilibrium. So suppose that the consumers in this economy have decided to increase the investment rate permanently from S1 to S2 here. So what happens to K and Y in this economy? The increase in investment rate then shifts the S curve to S1 curve to S1, and the current value of capital stock, which is K1 star, investment per worker will now exceed the amount required to keep capital per worker constant, and therefore the economy begins capital deepening process again, and this capital deepening will continue until the new investment per worker curve coincides with the investment required curve at K2 star. And from the production function, we know that this higher level of capital per worker will be associated with higher per capita output. So in other words, it means, so this at K1 star, the economy was producing output at Y1 star, but because of the capital deepening process and the outward shift of the investment curve, the K2 star per worker is required to produce output at Y2 star. In other words, what has happened in this economy is that the output has increased and the economy is now richer than it was before. This is the effect of increase in investment. When there is increase in investment per worker, capital deepening process takes place, and therefore there is an increase in the steady state value of K as well as Y. A second case is when there is an increase in population growth rate. When there is an increase in population growth rate, the line IR shifts inward from IR1 to IR2. So suppose an economy has reached its, so the exercise goes like this, that suppose an economy has reached its steady state, but then because of immigration, for example, the population growth rate of the economy rises from N1K to N2K. It rises from N1K to N2K here. So then what happens to K and Y in this economy? That's the question. At the current value of capital stock, K1 star, investment per worker is now no longer high enough to keep the capital labor ratio constant in the face of rising population. Therefore, the capital labor ratio begins to fall, and it continues to fall until the point at which the investment per worker curve is equal to the N2K curve at this point, let's say E bar at K2 star. And at this point, the economy has less capital per worker than it began with, and it is therefore poorer, and the per capita output is ultimately lower after the increase in population growth. So the per capita output has reduced from Y2 star to Y1 star. So it is ultimately lower after the increase in population growth rate. That completes our discussion of the basic Solow model. To conclude this lecture, let us go through some of the how to read literally the implications of the steady state growth model. In the beginning of this lecture, I was referring to this lecture by Professor Lands in the American Economic Association, in which he titled his lecture as "Why Are We So Rich and They So Poor?" So this is basically the developed countries side of the story as to why are we rich, why are they so rich and we so poor, or why are we so rich and they so poor. So the steady state value of Solow model is basically trying to answer this question, and these are the three answers to this question. First is that countries, and this is also how you can interpret the Solow's steady state value. First is that countries that have high savings investment rates will tend to be richer, other things remaining equal. So such countries accumulate more capital per worker, and therefore these countries have more output per worker. Secondly, countries that have high population growth rates will tend to be poorer according to the Solow model. A higher fraction of savings in these economies must go simply to keep the capital per labor ratio, per worker ratio constant in the face of growing population. Third is there that therefore the capital widening requirement of poorer countries makes capital deepening more difficult, and these economies tend to accumulate less capital per worker. And various exercises have shown that the Solow model holds up empirically. For example, based on GDP estimates of various countries between 1980 and 1997, if plots of GDP per worker against gross investment as a share of GDP and against population growth rates show that countries with very high investment rates tend to be richer on average than countries with low investment rates, and similarly countries with high population growth rates tend to be poorer on average. So at this level then the general prediction of the Solow model seems to be supported by data. And if we have to answer the question, how does the Solow model answer the key questions of growth and development? There are it answers the key questions in two ways. First is that the Solow model appeals to differences in investment rates and population growth rates, and perhaps to exogenous differences in technology to explain differences in per capita incomes. So to the question, why are we so rich and they so poor, according to Solow model, it is because the rich countries invest more and have lower population growth rates, both of which allow the rich countries to accumulate more capital per worker and therefore increase labor productivity. And the second question is, how does the growth rate that is achieved become sustainable in the long run? So why do economies exhibit sustained growth in the Solow model? For example, in the stylized fact number 5, which we were referring to in the context of USA, which has shown steady growth rates. The question is, why do such economies exhibit a sustained growth? The key answer provided by Solow is that because of technological progress. So without technological progress, per capita growth will eventually cease as diminishing returns to capital set in, and technological progress can offset the tendency for marginal product of capital to fall, and in the long run countries exhibit per capita growth at the rate of technological progress. So this in a nutshell is the basic Solow model, and with the discussion of the basic Solow model we complete our discussion on growth and development models, or the strategies of economic development and growth. For those interested in studying the Solow model in detail, you may refer to these references here. This lecture is largely drawn from Charles Jones' Introduction to Economic Growth, 2nd edition. This gives a very good description of the Solow model as well as extensions to the Solow model and this caters to a very wide audience. So those interested may look up this book. You may also try to read the original papers of Robert Solow titled The Contribution to the Theory of Economic Growth, and also Robert Lucas' paper of 1988 on the mechanics of economic development, which appeared in the Journal of Monetary Economics. I'll see you in the next class. Thank you.